This is Joe narrating a PowerPoint. It's Lesson 1 in Earth and Space Science, Structure of the Earth. It's on page 528 in the Kaplan book. The key concept in the study of Earth science is plate tectonics, just like evolution is the key concept in the study of life science. This diagram shows the structure of the Earth from the outside to the inside. On the outside of the Earth you have the crust, which is solid. Below that you have many miles thickness of mantle, which is more like a putty or a dough, so it has a consistency that it is capable of movement, and it is a higher temperature than the surface of the Earth. Further into the Earth you have the outer core, which is very hot and a liquid. It's so hot. And then in the center of the Earth you have the inner core. The inner core is also very hot, but there's so much pressure that it keeps the inner core in a solid state. Here's another diagram of the structure of the Earth. If you take a pie-shaped wedge out of the Earth, on the top you'll have what's called the lithosphere. That's the rocky sphere or ball of Earth that's on the surface of the Earth. It's composed of the crust and the upper mantle. The next layer is the asthenosphere, A-S-T-H-E-N-O-S-P-H-E-R-E, asthenosphere. That's the hot putty-like material that the crust plates will move around on. Further down you have the rest of the mantle, then you have the liquid outer core and the solid inner core. We know this structure is a good model of the Earth because of the seismic wave patterns that are created after earthquakes. So here's the theory of how the plates on the surface of the Earth move around on the Earth. There are currents of hot material bubbling up to the surface of the Earth, and these act like a conveyor belt, moving the crusts away from these rising points or down as the currents go down towards the center of the Earth. The Earth's crust is taken with it. Now, plate tectonics, or the movement of solid rock on the surface of the Earth, was an incredible theory. It was proposed in the early 20th century. It was not believed because it was so incredible, and also there was no mechanism to explain why the surface of the Earth in these huge plates would move around, and this is the model of how it works. So there's other evidence for the theory of plate tectonics. For example, from the geologic record, there's a model of how the Earth looked 250 million years ago. I abbreviated million years ago, MYA. At that time, all the land mass on Earth was stuck together. So the current continents are labeled on this map. Of course, they didn't have labels 250 million years ago, but there was only one land mass, and over time, these plates, each one in different colors here, moved apart. When these plates were all stuck together, it was called Pangea. Pan meaning all, Gea means Earth, so all the Earth was stuck together at the surface. So a gentleman by the name of Alfred Wegener, about 100 years ago, noted that the current outlines of the continents looked like they would fit together. So the coast of South America looks like it could fit into the west coast of Africa. So that was one interesting idea. And he hypothesized that the Earth plates were all stuck together at one time, and then these plates are starting to pull apart and are still continuously moving. So this is one piece of evidence, the shape of the outlines of the continents currently. So here again is showing how the plates would fit together 250 million years ago. They pull apart. Those separations in the plates fill with water, and you develop the Mediterranean Sea, the oceans, like the Atlantic Ocean. Another piece of evidence was that there were distinct bands of fossils found, and these bands cross continents. So, for example, in South America, you had a Triassic period land reptile that was found in South America as fossil remains, and also in Africa. You had fossil remains of Mesosaurus at the bottom of this diagram that were found in the tip of South America and also in Africa. Now, if these continents were always separated by a vast ocean, it would be unusual to have a distinct band of these fossils being found only in this one area of South America and this one area of Africa. But if the continents were stuck together in the past when these animals lived, it would make it easier to see that it was just one habitat for this animal that became fossilized, and then the continents themselves pulled apart. Another piece of evidence was the location of distinct rock formations. For example, there were distinct rock formations found in Brazil that matched the age of rocks found in Africa. And if these two continents were stuck together in the past, it would account for these rocks being found only in this one place on Earth and of the same time period. Similarly, there's rocks in the Appalachian Mountains of Pennsylvania, which are very similar to rocks that are found in Scotland. Another piece of evidence is the fact that there were found coal deposits in Antarctica. Now, Antarctica currently is at the South Pole. It's very cold. There are no plants growing there. Coal deposits are the remains of very old plants that have been buried into the earth and turned into coal. So if these deposits were found in Antarctica, then at one time Antarctica must have had a warmer climate, allowing the growth of plants. And Wegener's theory of plate tectonics theorized that yes, the climate was different in the past, but also that Antarctica was further north in a more favorable climate for plant growth. Another piece of evidence was found in the mid-20th century. Explorers were mapping the Atlantic Ocean, and they noticed that there was a distinct line in the mid-Atlantic Ocean. On either side of this line, the rocks had the same magnetic polarity. And as you move further away from this line, they developed a different magnetic polarity, but it was the same on both sides. So the theory is that hot rock that's in a liquid form called magma bubbles up to the surface of the ocean floor. When it cools, it acquires the magnetic polarity of the current existing Earth. And we know that the North Pole and the South Pole every once in a while will change location. So when the North Pole has a north magnetic polarity now, maybe 500,000 years ago it had a south polarity, and this changes. So as this liquid rock bubbles up in the mid-Atlantic, when it solidifies, it acquires a polarity of the then existing Earth's polarity, and it forms distinct bands on either side of this point where the rock is bubbling up. So the Earth's polarity switches roughly every 300,000 years, and it freezes that polarity into the rocks. And you can see on bottom it looks like a bar scan where the rocks on either side of the mid-oceanic ridge have the same pattern of polarity as they go from liquid to solid. This magnetic polarity is frozen in time, and it can be picked up with underwater devices that record the magnetic polarity of these rocks. So if you look at rock formations and surface landscapes on Earth, there are a couple distinct patterns caused by the movement of these plates of rock on the surface of the Earth. For example, as we just talked about, in the middle part of the Atlantic Ocean, there's a distinct line that runs up from Antarctica towards the North Atlantic, where the European plate and the North American plate are pulling apart. As these plates move apart, magma bubbles up to the surface and forms new rock on either side of this oceanic ridge. So this is still going on today. Europe and North America are moving apart by about 2 centimeters per year. And on this map, you can see the faint white line that goes down the mid-Atlantic. This is where the ocean floor is being formed by liquid magma coming to the surface and solidifying, pushing apart the continents of North America and South America from the continents of Europe and Africa. The previous map showed this divergent boundaries. Divergent means pulling apart plates happening in the ocean, but it can also happen on land. For example, in formations called rift valleys, where on land 2 plates pull apart, the land will sink down below the level of the land on either side. This has happened in Africa. If you look in the area of Kenya, you'll see the Great Rift Valley, where you have mountains on either side and the valley floor has dropped down in altitude due to the plate boundaries on either side of the valley pulling apart. And here's the Great African Rift Valley. The Rift Valley was formed by divergent plate movements where they're pulling apart, but there also are plate movements where the plates come together. In this diagram you see convergent boundary subduction. So convergent means they're coming together. Subduction means that one plate is going down below the other plate. On the left here you see oceanic plate. When that collides with a land plate, the oceanic plate is more dense. The more dense material will move underneath the land plate. As this plate moves downwards, it gets heated. The solid rock turns to melted rock or magma, and this may bubble up to the surface as a volcano. This is happening along many coasts around the world, and is still happening. For example, in the western United States, Mount St. Helens, which last erupted in 1980. On the left you see it before the eruption of the volcano, and on the right you see it after the eruption of the volcano. So it's still smoldering now. It is considered an active volcano. So this is a world map. On the left you see Asia and Australia, and on the right you see North America and South America. But there are subduction zones along most of these coasts, such that the oceanic plate is moving towards or colliding with the coastal plate, and the coastal plate is, the oceanic plate is going underneath the land plate and forming volcanoes. So along this red marked area you have many volcanoes and many earthquakes, because as these plates collide with each other, there may be sudden earthquakes as a result. This is called the Ring of Fire because of the volcanoes along this. Another type of plate movement, besides divergent pulling apart and convergent colliding together, are transform plates. So this is where one plate slides past another, and you might be able to see evidence of this in the roads. For example, the roads after an earthquake resulting from a transform plate movement will be no longer in line, or rivers might not be in line anymore. They might be shifted. An example of this is the San Andreas Fault in California, where plates are sliding past each other. The plates generally get stuck on each other and give way suddenly. This sudden release of energy causes an earthquake, and this is responsible for many of the earthquakes in California. Here's an aerial view of the San Andreas Fault. You can see the actual fault line running up and down in this picture, and you can see a road that's been shifted by movements of the plates in the upper part of this picture. We talked about convergent boundaries, where an ocean plate goes underneath a land plate, but convergence or coming together can also occur with two land plates. For example, India has its own plate. It had collided with the Asian plate, and it is still colliding with the Asian plate. When two land plates interact, you have mountain formation as a result. So the Himalaya mountains are the results of the Asian plate and the Indian plate colliding. That collision is still happening, and the Himalayan mountains are growing in height due to this active convergent boundary. So here's a diagram. 71 million years ago, the plate that is now known as India was off by itself in the ocean. It has gradually moved towards the Asian plate, and it is colliding with the plate, with the Asian plate currently, and the Himalayan mountains are the result. These are the mighty Himalayas, the tallest mountain range on Earth. They rise 6 miles from the surface of the ocean. There's also a type of rock formation that results from hotspots. So hotspots are not plate movements, but just single spots in the middle of a plate that have lava or magma bubbling up towards the surface. For example, the Hawaiian Islands are an example of this. You have a liquid rock, it bubbles to the surface, forms a volcano, lava continues to come out the surface of the volcano, expanding the dimensions of the island. That volcano might become less active, the plate moves underneath it, and when the magma chamber of the hotspot next erupts, it forms a new volcano and a new island. And this happens over millions of years, forming an island chain. So here's the third island being formed, and the plate is continuously moving over this hotspot. So here's the Hawaiian Islands. Down in the lower right, you see the Kilauea volcano. That's an active volcano currently. It's expanding the size of the big island of Hawaii. As you move towards the upper left, you see older and older islands that have been formed by older volcanoes. The plate is moving from right to left so that it's carrying these older islands towards the upper left, and a new hotspot will form underneath another island, and a new island will be added in the future. So this remarkable discovery of plate tectonics has come about in the last 100 years. The evidence for it is scientifically overwhelming, and it is the theory of how the surface of the Earth has formed and is currently forming. But there are some statements in older documents that attest to the pliability of even things like mountains in the face of very long time. For example, in Isaiah in the Old Testament, there's a quote, "For the mountains may move and the hills disappear, but even then my faithful love for you will remain." So even mountains cannot stand the test of time. And in the Quran, 27:88, you see this quote, "You see the mountains you reckon to be solid going past like clouds." So people have known for a long time that even mountains will wear down in the face of very long time periods. That's it. page 528, Kaplan book.